So I don't have a plan. Well, actually, I just made up a plan, but I don't have to do it. And the plan was just to go over the bonus problem, which I kind of did with you, but I didn't really do it right.
Okay.
Well, I did it in a not very nice way, and I remembered the nice way. I didn't remember it. I looked it up,
Okay.
and then I posted it on.
Yes.
It's sort of in the middle of a textbook, so it might not be the best instruction. So I could do that, and it would be very good practice, I think, review. I mean, for chapter 9. So
Okay.
does that sound good?
Okay.
Mm-hmm.
Okay, I'll do that. And so hopefully by Saturday, when I have office hours.
Oh, I wanted to tell you.
Yeah.
A lot of us, like 20 of us, are going.
Oh, yeah, you know.
Oh, that's right.
So I don't know if you want to message something in Slack, because if people aren't going to be here, I feel like you should
No sense in you.
come.
Yes. I'll post on there like, is anyone planning on coming to office hours on Saturday? This
Yeah.
Saturday.
Mhm.
And if
Mm.
one person says yes, I might be like, well,
What do you have?
But I feel like a
Yeah.
lot of the people that I see that come are kind of going.
They're
to
gonna
mountains,
go.
Okay.
so.
AKA the three of us.
Right.
Yeah.
I see. Okay, I'll post
I just don't
that.
want you to waste your time sitting here.
No, yeah,
on
I
a
understand.
Saturday.
Okay, so Monday then.
Mhm.
I'll okay, I gotta remember to do that. Anyway, on Monday, I will hopefully have a review for like a thing to do to review chapter 10, and then on Wednesday, hopefully I have a thing to do to review chapter 11. So I'm trying to like have it so you guys can get a review of all the chapters, and I'm not. Again, I still want to wait till I see what's on the quiz because I don't want to go over to teach everyone how to do like the things I did yesterday at the end with like the effective mass of electrons in a material, and you could do all this stuff for effective mass, but if it's just not going to be on the quiz, then I'm just going to stop talking about it. Anyway, so yeah, so I'll figure that out, but that's it. I will probably also teach class next week as well. Next week is about a different thing completely. I guess you don't need to know this right now. It's not really, but I'll just tell you anyway. Next week is about chapter 12, which is not on the quiz, obviously, and it's a little annoying that it's before the quiz. But chapter 12 is actually kind of fun. It's thermal physics. And it's actually a lot more understandable than any of the things in chapters 10 and 11 and 9. So it actually, I think, is the easiest thing so far we've done. So don't worry.
I understood thermo in college.
Okay, there we go. Yeah, it's more intuitive.
I get kept
There's not like you have to learn all these new like the exclusion principles. It's like kind of it's pretty intuitive. So hopefully it'll make fun of us. Anyway, all right, let's just move on. So the problem is it's just a quantum mechanics problem. And let's say I just told you the problem is solve or find this. So the problem would say like find the wave functions and energies. Or maybe like find the ground state. Let's say that would be a problem. Find the ground state for this potential of a wave function in this potential, and it would be like v of x. It's a one-dimensional system where it's 0 for x is less than minus a, and it's also 0 for x is greater than a, but it is minus v naught for minus a is less than or equal to x is less than or equal to a. Okay, so literally this might be, like if I was making a quiz for a quantum mechanics class, I would probably just write this, and that's it. And maybe the first thing you do is just draw the potential. So you have to be able to read something like this and know what it is, and of course, if we just label our axis with, okay, that's fine. This is the x-axis, this is the energy scale, and of course these are values in the energy dimension, right? And this is minus a and this is plus a. Then what this means is that that the potential is a value of 0 over here and over here, and it has a value of minus v naught, and this value here is minus v naught between those two things, okay? So, and this was so you did have to do this for the actual homework question, not the bonus, but the actual question involved you doing part of what I'm going to do. but I'll do the whole thing. And I'll do it again in case you did it on the homework without really understanding each part or something. And so, as usual, because we have sort of discontinuous potential, which is in this class, all we've done is discontinuous potentials. We haven't done anything where the potential is like a parabola or anything. That would be a very nice, smooth one called the harmonic oscillator. But anyway, in this case, because it's discontinuous, we might want to write our three regions, psi 2 and psi 3. So psi of x is the answer we want, but we might as well break into three regions because the Schrodinger equation is going to be very different in each section. It's not like we can plug in we can't plug in this entire function into the Schrodinger equation because there's many sort of separate values that it's sort of discontinuous. So if we write the Schrodinger equation again, we have, it's just d as opposed to a partial derivative because it's a one-dimensional problem of psi of x equals e minus v of psi. Of course, there's, you might see it the other way. Sometimes they'll write it with the v. I say this every time. They write it with the v on the left side. Whatever. It's just this. And e is a real number, obviously. That is it comes out of the problem because we're saying that this state, psi, whatever we solve for, has an energy E. We don't even know what it is, before solving anything. And of course, as we've seen, you find out that they have, things like expressions like n squared and have integers or whatever, right? So you find out what E is later. And this is just a derivative, second derivative. These are just numbers, right? So everything in here is, and V is our potential, which is the input of the problem. So the only sort of input of this equation is this V. And I should note that someone asked me about something about time. This is called the time-independent Schrodinger equation, which is the only one we're going to use in this class. There's one called the time-dependent one, which instead of E, you have a different thing there with a time derivative, but we're not going to deal with that because we're going to talk only about stationary states in this class. So anyway, now we just have to solve it. But because we have three regions, let's just pick the first one, which is psi 1. What is the Schrodinger equation in psi 1? So if I go to region 1, I get this. So d squared dx squared psi 1 equals E, but now V in the region 1 is 0, psi. So we get that. They're all functions of x, of course. Now, if we want to rearrange this a little bit nicer, we can move these things over here. Okay, so all I did was just rearrange where the constants went. M, E, and 2 and h bar are all constants. They're all real. They're all positive numbers, by the way. Actually, well, the E doesn't have to be positive, but no, E is positive here because E, the energy is going to be above here because it's going to be a free particle. Actually, sorry. Part of the problem is going to be that E is negative. I'm sorry. I said that in the most confusing way possible, but E is going to be negative, and the reason it's going to be negative is because if it's not, it would just be a free particle and then a free particle over a bigger well. It would sort of be boring. Like, you could still do it, and you would still be three parts and all that stuff. It would just not be the states we're considering. We're not going to get like a ground state or anything like that. So we actually have to consider the case where the energy is less than 0, but E is greater than V naught, than the absolute value of V naught. So in other words, the state is going to be trapped in this well. That's what we want. And the reason we want that is just because the problem tells us. It's not because, like, you could have any state you want. It doesn't care. It doesn't want to be in the well. It's just that if the energy is this value, it can exist freely in the well, but it can't exist outside very easily. So anyway, we get this, and what we're going to do is we are going to solve this, and the solutions look like psi 1. The solutions look like, well, because e is a negative number, okay, so this is the little thing I was doing before with what happens when e is negative. So because e is a negative number, I'm actually going to change this to absolute value of e and add a minus sign to make this a plus. Okay, all I'm doing is I want this whole thing to be positive. So 2 is positive, h bar squared, of course, is positive, because it's squared and it's positive. M is positive. I want e to be positive, so I'm just going to make it an absolute value and add a minus sign. Does that make sense? So now I have a function. Now let's just look at our differential equation again. I have a function whose second derivative is equal to itself times a positive number. What are the solutions of that? This is kind of like there's only two sort of types of problems we have like this. One of them is where the second derivative was the negative, and one of them is where it's the positive. If it's the positive, these solutions look like e to the kx plus b e to the minus kx. Right, does everyone remember this? We're using, there's no I here, because if we had an I and we plugged it back in, the second derivative would give us two i's, which would give us a minus sign, but we don't want the minus sign, right? And it just keeps things, it's easier to keep track of things if you know that everything here is positive, like that's the whole reason I changed this to absolute value. And now I wrote a k here, which is not anywhere in the problem yet, but really k is just this thing. It's actually the square root of this thing, because if you could just, if you're not sure about this, that's fine. You could just plug it back into this expression and take two derivatives and see what happens. If you plug this back in, take two derivatives, you'll see that you'll get that k squared has to be equal to this. So therefore k has to be equal to 2m e over h bar squared. And there's another advantage of the fact that I made everything here positive, is that when I put k, just h bar by itself, because it's under the square root and it's squared there. So another advantage is that now we don't have any I problems in here, right? That's actually the same. It's the same reason I just said, but it's another way to see it. Now everything under the square root is positive, so we don't have any weird imaginary number things. So this is just a label now. So the fact that I'm calling k this doesn't mean anything in physics. It's just literally a relabeling. I don't have to write it. So don't think of like, this is just a label I'm using for here, so I don't have to write it every time. I think when I did the problem before, I wrote it every time, which got really annoying. Okay. So does that make sense? Okay. Now, actually, I'm going to skip to 3. And so this is psi 1. Psi 1 is this, with k is this. And if I actually go to psi 3, I do this whole thing again, I get psi 3 is literally identical to psi 1. There's literally no difference. The potential is 0, so the differential equation looks exactly the same. The k is going to be the same. Everything's going to be exactly the same. Of course, the constants doesn't have to be the same because I'm doing a different problem. But so I'm going to use this, and this is psi 3. Same exact k. Okay, so there's psi 1 and psi 3. I'm using F and G because I want to use A, B for 1, C, D for 2, and I don't want to use E because E is energy, so I want to use F and G for 3. All right, so now I'm going to solve it for psi 2, and so it's basically the same, except this is for psi 2, except now V is actually minus V naught, so that becomes a plus V naught. All right, does that make sense? So all I did is just literally solve the Schrodinger equation, plug in what is my V in this region, in the region 2. It's equal to minus V naught, so this becomes an E plus V naught here. Right. Okay. Just a second. I'm a little concerned with my negative signs. Oh. Sorry. I wrote the Schrodinger equation wrong. This should be a plus. Sorry. It should be a minus v psi on the left side. And then I move it over here, it becomes a plus. Yeah, on the quiz, you'll be given a Schrodinger equation. So you won't have this type of problem. So the point is that now I have a minus sign here. But I'm actually going to take this whole thing, just like I did before, and make it positive and pull out my minus. Really, I'm just pulling out my minus sign. So I'm going to write this now as minus absolute value v plus v naught. Does that make sense? I know it seems like kind of a weird thing to do, but I just want it to be so that this thing is positive. So E is negative, so I'm turning it into minus the absolute value of v, which is the same value. And I'm factoring out this minus sign from this side, so it becomes this. So this number, absolute value v plus v naught, is a positive number, by 2, and is equal to that thing. It's the same thing. And we're actually, literally, it's the same exact process to solve it. We get the second derivative of something equals a now over here. So now it's going to be why do I keep what's wrong with these minus signs? So we should have 2m e plus v naught over h bar squared oh. Did I forget this minus sign before?
I had it.
And I moved it over. Is minus L. Oh, this is not. Yeah, that's really weird. What's happening to my signs? So this is e squared dx squared psi of x is this times psi 2. Okay, I mean, these are the right answers. So yeah, so we have a negative sign here, a negative sign here. This is a positive number. And therefore, we should now, it looks like, the problem is that it looks like this should be the exponential like this solution. And the other one should have a minus sign here. So the correct answer is that this has a minus sign, like that, but I don't know why. Why is this so? Okay, let me write the answer, and then we'll see if we can work backwards. So the answer is C, and this is going to be kind of e to the I something, but we can write it as sine of, and this is the thing I was saying before when I did it. It's better to write it as sine plus cosine. They're both solving the equation, the correct equation, which is not this one apparently.
It's because we're the real. Yeah, the real.
It's so. So in the PDF so I'm sort of trying to follow the PDF because that's how you do it. They keep e as a negative number, which is fine. but that's, I mean, it shouldn't matter. Minus yeah. And then oh wait, hold on. Oh wait, hold on. There's a problem here. So E plus V should be E minus V naught. This is a negative number, and V naught is a positive number. And I factor out a minus sign, and I get that.
Should V naught was a positive number?
Yeah, V naught should be a positive number.
Or should that not be? Okay.
Yeah, the potential goes to negative numbers, but V naught itself should be positive. I don't understand why this is causing so much problems. The point is that we should have, all right, let me move on and we'll come back. The point is that I want to define a thing called L, which is going to be 2m E plus V naught over H bar. The square root's only on the top. And it's basically the same, it's going to solve the same equation, it's just instead of E, we're replacing it with E plus V naught. Now, okay. The problem is that the energy, effective energy, should be the difference between these two. So it should be a negative value of E minus V naught, which is a positive number. So this number should be positive here.
Didn't you switch it last time?
I did switch it, didn't I?
Mm-hmm.
I went like that
Yeah.
and got a minus sign. Oh, so
You switched V naught and E.
so that's just always true, of course. But then, oh, this is painful. Literally, it's like literally a negative sign. I'm just trying to say that it's essentially just like a particle in a well with this depth, and this depth, how much is this? It's E minus V naught,
Mm-hmm.
which is E plus V naught, which is a positive number. And so that is just like that, which is what I wrote. And that cancels that minus sign. What is happening? I don't want a minus sign here. Somehow this minus sign goes over here, so I get a negative, and so I get a sine and cosine. Okay, listen. You can figure this out on your own. I'm sure it's an incredibly simple solution that I'm messing something up. In the book, I just want to remind you, if you look in the book, meaning in the PDF that I've sent called Finite Square Well 1, they use E as a negative number the whole time. They never use absolute values. That's probably what I'm doing wrong. I'm not going to keep dwelling on it because it's boring. Anyway, so we get something like this. L is some function of these things, right? And so then you get sine of Lx plus d cosine of Lx. So it's the exact same solution, but it's the exact same setup, but of course if we have an extra sign here compared to the other one, and the reason we have an extra sign is because here the energy was less than the potential, so the net energy was negative. Here the net energy is positive because it's above the potential. So in other words, if the energy is ever above the potential, you have a free particle that looks like a sine wave. And if the energy is less than the potential, you have a sort of exponential decay because it sort of doesn't have, it's sort of tunneling into it, but it doesn't have enough energy to like be a free particle over it kind of thing. So anyway. So anyway, this is psi 2, and that's it. And then so psi 1, psi 2, psi 3. And I'm just using L and K as substitutions for these quantities.
I'm good. It's just the pressure. Thank you.
This is the correct. This is what should be there.
So there's a neg.
So
You've switched something.
I've switched something. It's E plus.
So it's
Okay. I can always
Minus.
replace this. I can always replace this with minus V minus V naught. See, now it looks like I factor out a minus sign. I'm going to erase all of this,
okay.
and we're going to pretend that everything worked out.
So it's minus the absolute value of E plus V naught.
Yes, because what I want is that it's not greater than E. It's not. I don't want actually like the absolute value of energy plus the V. Like I don't want it to be double or whatever. You know what I mean?
Yeah.
I want it to be like a smaller number than like the subtraction between them. So I know it has to look like that.
Okay.
Dear God, this is
That was rough.
excruciating. Yeah, and that's not even the hard part.
Love
Anyway,
that.
so now here's where the
Rough
hard part is.
start.
Also, first of all, literally what's painful is that everyone did this on the homework already. So everyone else did it, and I can't even do it on the board. So anyway, let's move on. We have the boundary conditions, okay? And one of the boundary conditions is kind of tricky because it doesn't have anything to do with like the points where these wave functions meet, but we have to consider the fact that the wave function overall has to be normalizable, right? And if it's normalizable, that means that as we go to minus x equals, so as we go to x goes to minus infinity and x goes to plus infinity, we definitely couldn't have a wave function that blows up. And that's the reason I thought of that at all, and why even like who cares? Well, what are the chances it's going to do that? Well, the reason is because on the edges, which is psi 1 and psi 3, I have positive exponentials, which do blow up sometimes. So I got to be really careful. I can't, if I put x equals plus infinity here, this blows up, right? So this term couldn't be allowed if I have to do this to x equals plus infinity. But now let's actually analyze what we're doing. Psi 1 has to go to 0 at minus infinity. So if I plug in minus infinity for x, this is okay. This goes to 0, right? If I plug in minus infinity here for x, it becomes the minus signs cancel, and this blows up. So this term actually can't even be in this at all. It would correspond to a wave function that does something, and eventually, it can be as crazy as you want, but eventually as you go far enough to the left, it'll blow up to infinity because it's an exponential. And then therefore it won't be sort of normalizable. It won't be it won't be like contained in a region. So essentially what we require is that the wave function kind of goes to 0 at the edges. And the same thing for here. Well, which one is it going to be now? Well, as x goes to plus infinity, the wave function. So I'll write it as x goes to plus infinity, wave function must go to 0. And again, I'm talking about like it can't blow up, but it can't even do anything other than go to 0 though. It actually has to specifically go to 0 because you can imagine what if at infinity it went to like 1? Like what if I just said like plus 1? Obviously this doesn't solve the Schrodinger equation, but let's say I did that. That means that all the way, as you go up to x is infinity, you're always going to be basically at 1. You still can't take the integral and normalize it either, because if you take the integral over the function 1 from negative infinity to plus infinity, the answer is still infinity. So you're never going to be able to normalize it. So you can't even have things like that. So psi specifically has to go to 0 at infinity. And for the infinite well, which includes the quantum dots, which are 3-dimensional infinite wells, that's sort of already given for you because if it has an infinite potential, the wave function is identically 0 in the whole space. So we don't even have to really care about this in those cases. But in this case, this is a finite well, because the barrier is finite. We do have to consider it because the wave function is not 0 in these regions. So anyway, so as x goes to plus infinity, this term is going to blow up. So we can't have this at all. When I say can't have it, all I mean is that f has to be 0. I don't mean that anything weird, like nothing special happens to the exponential. It's not like, mathematically, the condition, you would just require that f is 0. Because, of course, any numbers f and g in this would solve the Schrodinger equation. So I'm actually free to choose them. I can't choose, I could choose any f and g I want. So choosing f is 0 still solved it. We're not doing anything crazy. So I'm going to erase them, but we had to use them to get to this part because we didn't know automatically that it was true. So g e to the minus kx. So here's what we have now, okay? So that's one boundary condition. Another boundary condition we have is that psi has to be continuous everywhere, and the derivative of psi has to be continuous everywhere. And now in the book, they use this kind of clever trick, which is that instead of dealing with psi 1, psi 2, and psi 3, the way we've set it up where minus a, like the potential is symmetric, so because v is even means symmetric around the axis, right? Then psi is even. Okay? So that sounds like sort of a weird theorem, like, oh, I have to use some special math to show this. And I guess you do, technically, have to use some special math to show this. But it's sort of obvious that, like, if there's no asymmetry, if around here it's a mirror image, the potential, the wave function, like, kind of has to be a mirror image. Because otherwise you'd be like, well, what's so special? Like, if you had a weird thing on one side and not the other, how would you possibly, like, where would that come from? Like, how do you decide what side it goes on? This is a very common argument, by the way, in all of physics. It's called arguments by symmetry, where you can just forget about huge classes of solutions because by symmetry, you know that it couldn't possibly be different on one side than the other, right? Left and right symmetry couldn't be broken if nothing in your problem breaks it automatically. So what they say is that because the potential is even, v is even, then psi of minus x has to be equal to psi of x. This is literally the definition of an even function. So mathematically, this statement means that because this is true, then this is true. And v of minus x, I erased it, but v of minus x, which just means the potential on this left side, v of plus x means the other side, and that's like that. This is also true of odd functions. If the potential was odd, means if v of minus x was minus v of x, then psi would have to be odd. But that would be a little harder to sort of imagine why that's true. It's not as sort of intuitive as like a mirror, right? But this is more common anyway because most potentials you'll see are even. And that's actually why when I did the problem before, I set it up so that one side was at x equals 0 and the other one was at a or whatever. Of course, that's the same physical problem. It doesn't really matter where I set them. But then I couldn't have used this argument. So that's why I wanted to change it too. Well, that's why I read the book and decided to change it. Okay, so in other words, what we're going to do is just use the boundary condition on this side. We're only going to do the problem on this side, and then we're going to, we're going to impose, I won't even write that. What we're going to do is do the entire problem on the right side for positive x, and at the end, we'll just say psi of minus x is equal to psi of x. In other words, we're not going to impose any boundary conditions at minus a, because once we solve the problem on this right side of 0, we'll just say it's just the same on the other side, which is true. Okay? And now you could do the whole problem on both sides, and you won't get it wrong. Of course, that will never be a wrong answer. It's just we're taking a shortcut. So the boundary conditions are, there's only two boundary conditions because we're only talking about this one point, which is that psi of 1, 1 is not in the game anymore. Psi of 2 at a equals psi of 3 at a. So it has to be continuous. We can't have a wave function that has some sine wave or whatever, and then it like completely cuts off and jumps to somewhere else and goes down. It has to be a continuous function. Otherwise, we couldn't take the integral and normalize it and make it into like it wouldn't make any sense if we didn't do that. So, and we also have that, and I'm going to write it as psi prime at a, because I don't want to keep writing d dx, but it just means the derivative with respect to x. All right, so this is continuous and the derivative is continuous. And the reason at the beginning of the first office hours or whatever it was, the reason I said this condition is a little iffy is because this doesn't apply if you have an infinite potential. And that's just I shouldn't have made a big deal about that. It doesn't really matter that much because when you're doing the only reason it matters is because when you're doing the infinite well, then if one of your solutions is like sine of pi x over L or whatever, right? This is one of your solutions. You might be worried that, wait a minute, the slope here is like 1 or minus 1, and then it goes to 0, the wave function. So it actually violates this condition. But it's okay to violate this condition if we have an infinite potential, right? And sort of the reason is because infinite potentials don't really exist. So this is like an approximation. So we're sort of breaking this rule because we're doing an approximation. Anyway, does that make sense? Was that more confusing, the fact that I said that? I just wanted, because he made a big deal that these are the two conditions, and then immediately did a problem where one of them is not true. So I just wanted to show you why that was the case. And it's because technically you can consider that the change in slope is like infinitesimally quick, and that's because the potential changes infinitesimally quickly. That's sort of a mnemonic way to think about it. Anyway, let's forget about this now. So we're still doing the finite well, so nothing's going to be infinitesimal now. It's a finite well, so everything's fine. So let's impose this first one. We get psi 2. Oh, sorry. I should mention, we actually now know something about this. If the potential was even, then we know that the wave function is even. Sine is not even. So no terms with signs in them can possibly be part of our solutions, because sine is not an even function. Sine is not mirror image of itself. Cosine is. So actually we know that c has to be 0. Right? That's right. It's d cosine Lx. Okay? So, sorry, I should mention that the turning point from where your homework ended and the extra credit started, in other words, where the techniques now you're hearing are going to be useful in general, but maybe not useful for the quantum mechanics problems you'll do on the, well, I would probably put this on a quiz, but just give you a bunch of hints and like, anyway, I shouldn't keep talking because I might have to make the quiz. Anyway, so
Keep talking.
So the fact that we knew that the potential was even, therefore the wave function is even, that's actually like that's not an obvious thing. So that's if you're like still a little puzzled about that, understood. If you're puzzled about any of the solutions, but except for the stupid minus sign, tell me. Whenever, you don't have to tell me right now, but let me know. You should be comfortable with solving the Schrodinger equation. But anyway, so let's keep going. So psi of 2 of A is this at A, which now I can just plug it in, is D of cosine of LA, okay? And that must be equal to psi 3, which is this one. And we're going to erase this because we know it's just equal to psi 3, right? But it's going to be a mirror image. So even the coefficient is going to be the same. So the G is still going to work on the left side too. Equals G e to the minus K A. Okay, and now let's do the second boundary condition, which is that the derivatives, I'll write it down here, the derivative of psi 2 at A, and so we have to take a derivative that will give us dl times minus sine of LA. Right, so I took a derivative with respect to x, and then I plugged in x equals a. So I got the derivative of, so I did the chain rule, in case you missed it, the chain rule of this would turn into minus, d is a constant, minus sine of L of x, and I plug in x equals a, so the L comes out. And the other side I have minus k times g still, e to the minus ka. Okay, so now these are my two condition. So I think this was I don't remember which part it said that you had to do for the. At some point, you could stop solving it because it kind of gets hard. But we do have two equations and two unknowns, right? G and so L and K are just, these are all things that we know. They're just things that were given. But G and D are just two unknowns. So we have two equations, two unknowns. It seems like it's probably not that hard to solve this. But you'd be wrong. It's actually kind of hard. So if we just divide them, which you can just do, then we get something like, well, the D's cancel, and we get minus, and now minus 1 over L. Cosine divided by sine is, maybe we should divide it the other. Actually, I'll divide it the other way. It's gonna be, obviously it's gonna be the same, just inverted. But so I'm gonna divide this divided by this. The D's are gonna cancel. So actually that doesn't even give us anything, but any conditions on that. So we're gonna get minus L, and then sine divided by cosine is gonna be tangent of LA. I should note that LA is actually a constant. So this is not a, this is just a constant. So it's not like a function anymore. And if I divide this, I get minus K G E divided by this. And actually this is just minus K. And I actually could turn this into tan of LA is K over L. So this is actually the conditions where you'd find where you'd find the solutions. And I'm actually so I'm gonna erase this for now. So now I'll go through the next. So the next part is, now this is all just, it would be very difficult for you to figure this out, like by writing it on paper. Someone figured it out, but I'll tell it to you because it's actually kind of interesting. It's a sort of a graphical solution. So we're going to define a variable called z, which is equal to LA. So it's that one. And we're going to define another variable called z naught, which is equal to a over h bar radical 2m v naught. And you can see, maybe you can see why this z naught is like related, because 2mv naught square root over h bar is kind of like, it's not equal to this, but it's equal to some kind of function of this, because K and L both, I erased what they are, but they both have e's in them. They both have 2m e's in them, but only one of them has a v naught. So that's kind of like the difference. So if you could figure out how they relate if you just do some algebra, how z naught is related to K and L. But then you get that this turns into tan of z is equal to, and this is actually, so this is the relation, z naught over z squared minus 1. Okay. So this is, again, this to get from this equation, which is just following from our boundary conditions, dividing them, to get to this, all you have to do is just, there's a change of variables that you just have to, you know, if you really had to do this on your own, you could just play around with them and figure this out, I guess. But then if you just rearrange them and actually plug in what K and L are and divide, you can get this relation. Now this is what's called a transcendental equation. So, which means that it's impossible to just find a solution like analytically. Well, it's not impossible; it's just very hard. And the way you can solve this is you can graph this side, and then graph this side, and then see where they intersect. Isn't that like really? That's kind of crazy. So what we're going to do is just say that y equals this side and y equals this side, and graph y over z. I'm actually only going to plot the positive values of all of these because LA is a positive number. So I can only have positive values of z. Then, so this axis is z. And now let's just pick a point called z naught. Now z naught actually depends on v, right? So actually, depending on how big your potential is, z naught could be different. So let's say z naught is this. this side. So actually, let's do this side first. This is tan z. Y equals tan z. So tangent, if you remember from trig or whatever, looks like this, and then has a, and then looks like this, and then has a, right? Does that look familiar? Okay. And then maybe it looks like this. I'll erase my z naught for now. Okay, so this is the left side. Now, what's the right side? This is, again, it's a complicated function. There's sort of no way to figure out what this looks like. But if you actually plot it, where, let's say this is z, let's say z naught's here. It's a value of z. It actually looks like that. So it looks kind of like 1 over z near z equals 0. It kind of looks like it goes to infinity like this. But then it stops and it crosses through, because if you plug in z equals z naught, this becomes 1 squared minus 1 is 0. So again, why it looks like this shape, you could think about for like an hour and maybe figure it out, but it doesn't matter. The point is, this is what it looks like. Now you'll see there, and there, they cross. And if they cross, that means that I have a solution to this equation. And in the specific case I did, where z naught was equal to that value, okay, what did we get? We got 3 solutions, and that's it, because tan is going to go this way and the thing is going to approach. So there's only 3 solutions. What that means is that there are 3 bound states. That's, okay, don't write this down. Don't write 3 bound states down, because I just made up where z naught goes. That means there's 3, okay? If z naught was a different number, then I might cross more of these lines and I would have more solutions. So this is showing you that I gave you a potential and I just gave you an energy and a V naught, or the V naught. And you might think, well, it's just like the infinite well, there's like infinitely many solutions because it goes like n squared, you can just make n whatever you want. Or the 3-dimensional one, you could have 1, 1, 1, you have 1, 2, 1, you could have 6,000, 5,000, you can make, it goes on forever. Because this is finite, there's not an infinite number of solutions. There's literally only solutions where these intersect. Okay, so there's literally, if z naught was just happened to be this, there would be exactly 3 bound states, and that would be it. There's only 3 energy levels here. And of course, to find what the energy levels are, you could find what z value this is and then plug back in to here and solve for L, and L has E in it, and you could solve back for it. That would be a lot of work, of course. I'm not going to do that, but here's some, so now, okay, great, who cares? But the cool part is that there's some interesting limits. What if you had z naught to be as small as you could? So I'll erase this curve. So the tan curve is sort of non-negotiable. It always looks like that. But if I put z naught to be, actually, if I put A was really, really, really big, oh yes, here we go. Now, okay, here's the cool part. Now, what if I have a wide, deep, actually, it doesn't even have to be wide, a deep well. What if you took, so this is the solution, and the reason I'm going further with besides you think we have the solution, what's the point of going? The reason is because this is not a very interesting, like, oh cool, there's graphs and you can find intersections, but what do you use this for and how do I know it relates to anything else? What if you had a really deep well? A deep well means that V naught is very large, right? Deep well means V naught is, I'll say it goes to infinity. It just means large. Of course, it can't literally be infinity. It doesn't make sense then. But V naught is large, then Z naught would be large. If Z naught's large, then you would get that your thing would go like your plot, and I'll say it's way farther out here. Your Z naught would be here, and it would go up very high, and it would cross all of the tan lines. That's funny, tan lines. No, tangent lines. It would cross them very high up and very close to their asymptotes. What are their asymptotes? These are at this is pi over 2. This is at 3 pi over 2. If you remember that, wait, is that right? Yeah, 3 pi over 2. Remember about tangent, they are undefined at 90 degrees, 270, right? They're defined at n pi over 2 for n odd. That's where they're undefined,
Yes.
right? So if I have the z naught be very large, this side of the function when I plot it is going to go up really, really high, and it's essentially going to cross, because my tangent lines go like this and get really close to n pi over 2 for n odd, it's going to cross, like I'm drawing this not to scale, but it's going to cross it very close. So what that means is that if I try to find En plus V naught, which is sort of the total energy above the bottom, you'll get if you solve for so your solutions have solutions have z close to n pi over 2 for n odd. Okay? And then if you solve this, so L, remember, was radical 2m e plus v naught over h bar, right? If you plug in z, so this times a is z. If you plug in n pi over 2 here and you solve for e plus v naught, you'll get, and I'll just save you the trouble of, you'll get that. So what is this? This is literally the energies for an infinite square well. Right? We have n squared, pi squared, h bar squared over 2m times, and then I put 2a squared in parentheses. This is literally an infinite square well with a width of 2a, and these are just the energies. Isn't that cool? And that we got that from this finite square well where we take a limit, and this side, where the intersections are now going to occur because it's so big, they're going to occur near the zeros or the asymptotes, thank you, of tangent, and therefore if you plug in those values of n and you solve for e through this first equation, you'll get literally the exact solution that we got for the infinite square well.
Okay.
Isn't that cool? I know.
Nifty. You lost me in the middle, but you brought it back around.
Okay, good. The point is that we've recovered something that we already knew. And it's literally the limit of this finite version.
Cool.
So, of course, the finite version, as you see, is very complicated, but...
So when it gets deep enough, it's basically like an infinite square.
Exactly. The energies show that it is, yes. Energies above the bottom. And if it's shallow, the other limit we could take is what if it's really shallow? Well, if it's really shallow, that just means that, or really narrow, you could also have it be really narrow, we would get that z naught would actually be like really, really low. And you actually see that because tangent goes through 0, no matter how low we pick z naught, it always has to cross once. So there always has to be at least one bound state. No matter how shallow or how thin you want it to be, there's always going to be at least one solution, which is kind of interesting. Because you'd think, oh, eventually it would just never be able to be trapped there. Like if you made it super, like if you made it like really narrow, you'd think, well, it would just be like a free particle and it wouldn't even notice, right? You'd think, oh, it doesn't even notice that there's a thing there. But in fact, you'll see that no matter how small you get, you have to cross this at least once because of how tangent works. And so you have to get at least one bound state. So that would be an example of a quantum system with one energy level, which would be kind of boring. But
I think we have different definitions of boring.
that would be boring. But anyway, okay.
Nifty.
So isn't that fun?
Super.
So you could always take limits. As I know, like last semester, we talked about limits, right,
Yeah.
with the ramps, and if you take the limit as the ramp goes to 0, with the friction, right?
Mm-hmm.
Same thing works here. They're obviously a little more
Just
complicated, but they still work. You should get the same energies because a finite square well with very large depth is literally just an infinite square well, and just by rearranging, you can literally get the formula back.
Cool.
So this would be the inefficient way to find the infinite square well solutions.
nice.
All right, isn't that nice? So what else do you want to do?
A question.
Yes.
Yeah, take it away.
So based off of this, when a quantum particle is traveling from the left
Yeah.
in figure 9, so what you have up here,
This one, yeah.
yeah, with energy E
Uh-huh.
less than V naught, write down the Schrodinger's equation
Yeah.
for all 3 regions
Yes.
and find the equations that will allow you to determine all the constants in the
Yes.
wave functions.
Yes. That was all of it up to here.
Okay.
Beyond here is just finding the specific.
So that question is, which is on the homework,
Yeah.
is exactly what he told us to do for number 9, kind of.
Yes. Yeah, this was literally the homework question up to here, and then the extra credit was literally this.
Yeah, but this is another for this week's homework.
Oh.
It's number 11 if you want.
Let me make sure it's the same.
So this was 9, and then that's 11.
He's okay. Oh, I see. Oh, okay.
Since we're talking about
Yes, thank you. You're absolutely right. That. Oh, actually, hold on. Yes. Okay. So the difference between this was literally a question 9 from the homework. Question 11 from this homework is, remember at the very beginning I said, what if you had the energy greater than 0? And it would be kind of boring because it would just be a free particle and then it would be a free particle with different energy. That's question 11. So question 11 is the same in regions 1 and 3. It's identical to this.
Oh, when E is greater than.
When E is so all they want there is because they say traveling from the left. That's the first few words of question 11. So it's traveling from the left. They mean a free particle traveling from the left.
Write down the Schrödinger equation for all 3.
So it would be the same 3 regions except it's going to be actually the solution is going to be the same in all of them. So actually, let's just do that.
Do not solve the equations. You don't have to tell me twice.
You could solve. It wouldn't be that hard. But anyway, actually, okay, it would be a little hard because it's not a bound state.
he's erasing what I did.
Okay, well let's do that because
That's right here.
the only reason I'm doing this with you guys is because I think that when you guys, well, not about you guys, but when some people in the class read that problem, they think it's much harder than it is. So I want to show you how not much harder than this it is. Actually, it's much easier than what we just did. So, and remember the first day that I think you guys were all here. The first day that I talked about quantum mechanics, I was saying that there's basically 2 types of solutions to Schrödinger's equation. There's free particles and there's bound states. I called them stationary states. Actually, maybe it was just you here. I don't know.
Probably.
Or something. Anyway, there's bound states and free particles. The one we just did was a bound state because the energy was less than 0. That's basically what it means. Now we're doing the exact same problem, but the energy is going to be greater than 0, so hopefully I can do all the signs. This is still minus V naught, that's fine. We'll still make this minus A and plus A, because why not? And a particle is traveling from the left, and that's it. Okay, now we still have the 3 regions, 1, 2, 3, and in regions 1 and 3, everything's going to be identical. Let's solve this again. We've done this exact thing for the free. When I did the free particle before, I think it was on the first homework. We did this exact Schrödinger's equation, so I'll just write it again. plus V. Let me look this up because now I'm getting paranoid about all my signs. Oh, wait. No. That was what I did wrong. Okay. Do you remember this that I wrote at the very beginning and then I changed the sign here because I said it was on the other side and then I was right the first time and I was just reading because the problem uses a negative V naught. So I was reading the problem wrong.
Got
So that actually solves literally the issue I just had in the last problem.
Sweet.
I know no one cares about that anymore except
That
for me,
makes
but
sense,
anyway, that's why. So this is, again, as I keep saying, you will be given the Schrodinger equation. So you will not have these issues. So for a free particle in regions 1 and 3, V is 0. And so we again have just, this is literally, so, you know, you're getting sick of this, I assume. Be doing this over and over again, but we get this, and now we can write 2me minus 2me over h bar squared. We get this again. This is again, as always, this I'm going to call k squared. So therefore, this becomes, so I'm just writing it in a different way than I just did, but it's literally the exact same thing I've been doing. Minus k squared psi. Just keep in mind that when k squared is actually just this part. So I should really write like this, not the minus sign, because I'm going to keep minus k squared. So this is my differential equation now, as long as I assume k, so I can kind of keep it in the back of my mind over here. 2me over h bar, and I don't have to worry anything about, I've been worrying about the sign of e, but because e is positive in this problem, I don't have to worry about any of that. I don't take any absolute values, everything's fine.
Got it.
So this is my differential equation now. We know the solution of this, it's the second derivative of some function is minus some constant times that function. This is sine cosine, right? It actually is going to be easier because they're talking about particles traveling to use this form. We're going to use the imaginary form. Of course, it's the same, but we're going to use this form because when they say traveling to the right, you can't. It's harder to write that in terms of sines and cosines because a sine wave is everywhere and a cosine wave is everywhere. So it's a little hard to. So traveling to the right means we're actually just going to use this part. So this is psi 1. This is literally the answer. So when they say a particle is traveling to the right in region 1, find the wave function in all 3 regions. We just did this one. We actually also just did
3, right?
3, exactly. It's exactly the same, but of course the constant is going to be different.
Yeah.
So we're going to get, I'll call it f again. E to the I, k, x. And again, it's traveling to the right, so we don't have to use the g, e to the minus I, k, x, or anything like that. So we're like 2/3 done, basically. So now all we need is psi 2, and I'm actually going to just modify this one, because psi 2 is going to be this, but now we're going to have e minus v.
So wait, did you just erase the e sign?
Yeah, so now we're doing 2.
Okay.
So I don't want to rewrite it, but it's the same. Of course, the left-hand side is the same, yeah.
Okay.
So, and now this side is going to be, well, it's e minus v, but v in region 2 is minus v naught. So this is going to be e plus v naught. Those are both positive numbers. Psi 2. Okay, and now this is, okay. So now, I have to erase k, because it's not going to solve it anymore. Now, the only difference, this is still a positive number, so there's no weird things happening. The only difference is now I have that. And now I can't call this k anymore, I can call it L now, where L, this is the back of our head, is this region. 2m e plus v naught, h bar, and this is L squared. Now we have this. And that doesn't mean this anymore. So the only difference between region 1 and 3 are identical. Region 2 is only different in that my energy is now changed to E plus it's E minus a negative number, so it's E plus V naught. So if I just literally make those changes, there's no sign changes. Everything's identical. It's not like the last problem we did where the sign changed and then we have a different function. Like we have, in the last one we had a standing wave in the middle and a decaying exponential on the edges. Now we have standing waves everywhere. It's just that they have slightly different values here. And so we get psi 2 is absolutely identical, but with an L instead of a K. So psi 2 is going to be C e to the I L x. And I don't write the other one because it's going to the right still. So that's it. So, and because they say don't solve them, I guess we don't solve them. But if you wanted to, I know you're just, Keegan, please solve them. No, I'm not going to do it, but you would just set them equal at the boundaries. Essentially, you would just get that they look
Like you did back here.
like this, and then this would actually, well, sorry, it wouldn't necessarily, well, I'm actually not sure. I would have to do it out, which we could do. I think it would be larger and would have a higher frequency. And then here, I don't know, something like that. You could look it up if you want. The point is that because here it has some amount of energy, over here it actually effectively has like a little more energy. This is just like a free particle with total energy E plus V naught, right? So it just, and having more energy makes the frequency L higher. I guess that's it. And then on the other side, we don't necessarily know what happens. Again, because we have an F here and an A here, we don't have the same, actually, no, it's symmetric. So the same reason as last time, it's symmetric. So actually, we could even, if we were super clever, we could replace this with A. I don't think you'll have to do something like that, but so we could actually say this is going to be identical.
So we don't have to do two different.
Yeah, so the only reason I know it's A is because the whole problem is symmetric.
Got it.
But
the other problem, it wasn't.
no, that was as well.
Oh, okay.
Yeah, you don't have to know to do this. I don't think for like a quiz because that's like a very special like math trick.
Oh. Okay.
And the reason is because if V is symmetric, which means even, then
oh, and that's the
psi
hint he
is
gave.
even or symmetric, whatever. What's that?
That's the hint he gave for the last number 9, didn't he? He said like two
Oh.
equations are even and one's odd. Didn't he get?
Oh, he just mentioned that because there was this.
So
yes.
that doesn't equate to what you're talking about then. Because if
Oh.
two equations are even, then wouldn't, to go with your point, they're symmetric, then they're even. Or are we talking
That's a
about
good
two
point.
different
No.
things?
That's a very good point. Huh. I'm not sure.
I'm not
That's an
either.
excellent point. In the other, okay, I remember in the other one, you got the 3 states you got, or the lowest 3 states you got.
Yeah.
Were like a sine, or no, it was like this, and then this, and then this. And this one and this one are symmetric, and this one is not, is odd. So these two are, you're right that if the potential was symmetric, why should you get any anti-symmetric? I'll think about that. That's really interesting. I mean, because if you do the problem where one end is at 0 and one end is at A, then this is not symmetric around 0. So this is not even anymore.
Mhm.
So, but obviously that would be kind of a silly thing to do because you might as well put it symmetrically around the center. That's interesting. You know what? I'll think about that. There's probably a subtlety that I'm missing about this statement.
Okay.
But you're absolutely right that yes, we did get an odd solution, 2 even and 1 odd solution, and the V was even the whole time.
Yeah.
Okay. think about that. Anyway, if we weren't sure, which I guess we're not now, you could just leave it like that.
Okay. Cool.
Yeah. Okay. Do you have any questions about this one? So, if it feels like we're doing the same thing over and over again, that's because that's kind of what quantum mechanics is.
Okay.
You just do this. This is literally the same equation. You do it in several regions usually. There's way more interesting stuff where you use all these other techniques that we're not going to do. But I'm happy to show you. Just say the word, and I will show you. Just blink. How about just blink and I'll show you?
I have
I'm just
a
kidding.
question on one of the homework questions.
Yes. Go ahead, but okay, just go ahead. Tell me what it is.
So it's chapter 10.
Okay, that's not what I wanted to hear.
Sorry.
No, sorry. What was it?
It's a quick question. Okay.
Today.
So it's asking us
Today?
to find the
Sister one.
Oh, yes.
so we need to find the velocity basically. Now I have the velocity equation, but I'm confused because you don't need to use a wavelength in there, or do you have to find the change in energy in order to do this? But I'm confused because it also talks about a photon and an electron. So this is what I started
Yeah.
doing.
Yep, you can
Can
find
we
the
change
energy.
it?
Sure.
Well, it gives us this energy though, so that's where I'm kind of confused. Do we
Oh.
do the but then I was wondering in the velocity equation, you don't need wavelength because it's just the mass of the electron and the energy, but the Fermi energy, right? But then I was wondering if you needed to find the change in energy.
Yes.
Because
Here,
of
let's do this one together because there's a few concepts here that I think. This
Is
is
it kind of on the right path or no?
yes. I
Okay.
believe you actually have all the pieces there, so you essentially have the answer.
Okay.
But I think you need to subtract
The
the work function from that energy, and then you have the answer.
okay, that's what I was wondering. 'Cause I
Okay.
was like, why do? Because I was like, I have the wavelength, so I think I need to use it.
Yes.
And
So-
that's where I was going to subtract. Okay.
Right. So it looks like this, and I don't know why they even draw this, but this is the Fermi energy. This is energy
Correct. Yeah.
E, and this is the work function.
It's 1.5.
Oh, and this is okay. So this is a metal.
And then
Obviously,
that's-
obviously it's a metal because it's has a Fermi energy,
Yeah, then
and this
that's
is the vacuum.
Yep.
So to get an electron out of this metal to the vacuum, being hit by a photon, it just needs to jump up to this much energy, and then it has the leftover energy. So the kinetic energy of the electron is going to be energy of the photon that. So this is the energy it gets.
Okay.
Minus the work function.
Okay. So you need to use then the mass of the photon.
Well, the photon has no mass.
Oh, it says a photon. Oh, is absorbed by an electron.
Yes. So
Okay.
the electron. This is the electron. Sorry, you're right. It looks confusing. So if you're taking an electron from the Fermi energy, and you want to give it, so electron is at E Fermi in energy. Then you hit it with energy level E photon, which they told you the lambda, so we could of course easily just solve for the energy, right?
Okay. Yeah.
And so it starts as E Fermi. Actually, we don't even need E Fermi for anything because.
Well, you need it for the velocity equation, right? Because that's square root of 2
Oh.
mass E Fermi.
Actually,
Or is there another velocity?
no. I think we don't need it because all we need is that the electron had. If it was at the Fermi level, it had no extra energy. It was just like sitting there.
So it's at like ground.
It's at the ground state in the metal, yes.
Okay.
And therefore, if you hit it with, so electrons at E Fermi,
Yeah.
hit with photon with E photon, which you could easily solve by the lambda they give you.
Uh-huh.
So this is 1, 2. Let's just number them. Then it has energy as long as E photon is higher than the work function is just to get it out of the material, right?
Okay.
As long as it's higher, then it has leftover energy, E photon minus this. And the leftover energy is
What you're going to use.
kinetic energy, right, which is 1/2 mv squared, I guess. Or p squared over 2m you could use.
Okay, so. So couldn't we just take the energy and use the velocity equation? Or is that
Which velocity equation?
Equals p squared over 2m.
Yeah, that's the same as this, yes. This is,
oh yeah, because it's just square root, right? No.
if mv is p, then that's the same thing. Yeah, you could use either one.
So the equation I saw was no, oh yeah, that one. PF over M. Is that not the one?
Oh. Yes, you could use that too, but then you need p, and you could solve for p just by this, which is it's the same thing.
But couldn't you just use the square root of 2m EF over M? Because that's what it says.
Square root of 2m EF. No. We don't want to use EF anywhere here, actually.
Okay.
You could use that. So actually, let's just, if we put the whole thing together. This. So I just solved, so this is the leftover energy.
Yeah.
Which I set as KE, and I just solved for V. So I didn't use P anywhere here.
Okay. Oh,
And I didn't
so
use
then
E
you-
Fermi either, actually.
So,
And the point of the Fermi part, like the only...
so why
yeah.
don't you need massive electron in the top part of that equation?
It's here.
Okay.
It's because it's this, and I just moved 2
Oh,
over
you
and moved
just-
M under. I just rearranged.
Oh, okay, okay.
Yeah, that's the same thing. Sorry, it's not a new equation. It's the same, yeah.
Okay, that makes sense.
So I should mention the reason that E Fermi is in the problem at all, even though we don't use it, is because they just want you to get used to the idea that if an electron is sitting at the Fermi level, it's in the ground state. So even though it's sort of above the lowest, like it's not at the lowest energy level that like remember the whole Fermi sphere thing? Or actually just the bands, how you pack them in like this. Even though it's not, this is the lowest energy, if something's sitting here, it actually has 0 kinetic energy. So the whole point of this problem is saying that all the kinetic energy you get by ionizing a metal is given by the energy you give it minus the work function. The work function is just to get it out of the material it's in, or like any bond it's in. So if it's at the Fermi level, they're just telling you automatically that it has no extra energy. It has no kinetic energy. Because the Fermi level is defined when T equals 0 at temperature 0. There's no thermal fluctuations, everything is sort of settled. So that's why that's confusing, because they tell you E Fermi in the problem, and yet you don't need it to solve for anything.
Okay.
So I should write, I guess. Let me write electron at E Fermi has 0 kinetic energy. This is sort of the lesson of this problem, I guess. The lesson that's not involved in solving it. And then this problem is actually literally identical to a problem we did last semester with a work function. Remember, the first time we learned about work functions. Yeah.
That's what very nice. This looks very nice.
Yeah, and it's very tempting to write it and be like, this can't be this easy. They gotta use something with the Fermi, whatever. But in fact, they're just sort of telling you that's the ground state of an electron in the metal. You could also talk about doing the same thing, ionizing an electron, but it could be like one of these electrons. But then you'd have to give it enough energy to overcome that much to get to the Fermi level, plus whatever else you need. So in the problem, they say like, what's the like maximum energy? I think the reason they say maximum energy could have, or maximum velocity, they say. The reason they say maximum velocity is because we're considering that it goes from some level to the vacuum, which only requires the work function. If we had to like, if it was here, and we had to go up this much energy plus the work function, then we'd have less energy left over. So we're sort of considering the best case, which is that it just happens to be at the top, which kind of makes sense because if you're going to ionize a thing, it would more, it's going to hit the outer ones first, basically, in the space.
So it assumes it's at the Fermi level, like the
So-
electrons.
yeah.
It assumes it's at that level.
Yeah, when they say it's at the Fermi level. Yeah, and so I guess if they told you just in general this situation, an electron is ionized, we wouldn't actually even know. They would have to tell us it's at the Fermi level for us to know that all of the energy it costs to get out is just the work function.
You look confused.
No, just this question's stupid.
Okay.
Sorry.
I agree. I don't even know what you're talking about.
Right, number
Yeah.
7. Like, are we just gonna Google that? Like, what? Why do we need to know that?
Explore additional applications of this quantum well heterostructures. Interesting. And their use in devices. Yeah, that's you could just Google it and write something down. I don't really care. But I'll just say what those structures are. Heterostructures means structures where it was the thing I was drawing, or I don't think I drew it, did I? No, it was on the. Maybe I drew it. Anyway, it was the thing where you have. Oh, sorry. It was the thing on the slides. I drew it the other way. Where you have. If this is your z direction, you have a layer with one material and a layer on top with another material, and your layer in the middle has a slightly different gap,
Yeah.
so that electrons can actually kind of flow easily with overcoming a small gap.
What is it, a two-dimensional gas or something?
Yes,
like
and
that?
it becomes a 2D electron gas because it effectively behaves like free particles in 2 dimensions because they're trapped. In the z direction, it becomes an infinite square well. It's actually not infinite, it's finite because there's still gaps here, they're just big. So it's like if this is an insulator, and this is an insulator, okay, what that means is that the gaps here, if I drew the Fermi level, the gaps would be really big, right? But in here, let's say it's like a semiconductor or something where the gap is very, very small, or just a metal, let's say, right, where you could very easily go between the gaps. Then the electrons in here would be basically free, but if they tried to get into here, it would be like they would have to cross a big well. So this is where like there's like 3 dimensions of energy happening at this time. But anyway, you see that these ones, if it has a gap, trying to go into here would essentially, if you plotted it in the z direction this way, you would basically have this. So this is v equals infinity. V equals, of course, it's not actually infinity. It's just whatever this gap is. So I'll call this. Actually, no. I'll call this EG1, EG2. G means gap. So this would actually be a finite square well like the one we just did. But now V is EG2. And on this side, let's say it's bigger. V equals EG1. Does that make sense? And in the middle, there still might be a gap. So it might actually be like, this. So this is E equals 0, and this is V equals EG3, where this small one is EG3. So in other words, in the Z direction, in the sort of sandwich direction, right, it's basically like a finite square well. Obviously, I'm exaggerating how this is like a really badly designed one, I guess. But imagine that these are really high compared to in the middle. So effectively, we get, as we kind of did the whole problem, but we just saw if we made it really deep, if you just tuned these materials so that the potentials were huge at the edges, you would get basically like your few wave functions and your few energy levels in here, right? And they would be like n squared, pi squared, h bar squared, blah, blah, blah. So that would be your Z component of your things. It would just have energy levels in Z, but in the X and Y directions, it would be literally free. And X and Y is this way. So this is X and this is Y and this is Z. So in this plane, it would be basically like if you made it really thin, of course, it would be like a two-dimensional gas. And that's useful for, I don't know, something. Apparently it's really useful. And then that's where you get the result of it. So this is on like the last slide of that thing from yesterday. The energy of the electrons in this gas are nz, which is this level. This is the level nz. Nz squared, pi squared, h bar squared over 2m d squared, where d is actually the thickness. So d is the thickness of this layer because it's a z infinite square well, effectively. Of course, as we just saw, it's not going to be exactly because it's finite, but we just saw in the limit, when you make that stupid little graph thing like really big, you get this limit. So it's effectively this plus the x and y kinetic energies, and those I can just write as p squared over 2m, which at p is h bar k, remember? But this time, this m is not actually the regular m. I know it seems like, oh, this is the answer, and I say something else, but where m is actually the effective mass, which literally means sort of the inertia. If you push it, it's like how moment of inertia was not just the mass of the thing, it was also how hard it's really how hard is it to rotate. That's like just like this. This is how hard is it to push these electrons around. It's not actually just as easy as pushing a regular electron in free space. And the reason it's not as easy is because they're actually in bands. They're not freely moving on their own. Because they're in bands, you have to sort of push it up this hill kind of thing to get it to have some momentum. So to give it some momentum and put it here, where this is k space, this is momentum, to give it some momentum, you actually have to cost it some energy. And momentum costing energy is that's literally what mass is, but it's not usually determined by like some band structure of a material, but you'd have to solve all this Schrodinger equation or whatever, or just get this, and you could find the effective mass, and that was that point of that. So the point of that is that an electron in a 2D electron gas trapped between two materials, so the sort of point of that problem, which of course you don't have to do any of this to get the answer to that problem, but the point of these is that, and I'll summarize it again real quick, is that you have a material in the middle that is relatively conductive compared to two insulators, such that in the z direction you basically get an infinite square well, and in the x and y directions you get a free particle. And free particles have kinetic energies equal to p squared over 2m. So these are the x and y directions, where m we have to be careful of because m is the effective mass of giving something, giving a particle which is now trapped in a band. It's not free to move and have any k and any e it wants. Or I should say any momentum and any energy it wants. It's not free. It has to follow the bands, right? That's literally what a band is. It's a relationship between momentum and energy. So to give it some momentum costs some energy. Using that relation and the second derivative, that kind of stuff, and basically it's essentially F equals ma again, we can find m, the inertia, right? And if we find that inertia, that becomes an effective mass, which goes here and here. So effectively they behave like, and usually this is much bigger than the electron mass. This is heavy. Because pushing electrons around when they're trapped in here is not just like pushing free electrons around, it's pushing these things through these weird bands and giving them energies, and it's sort of like it's like in a molasses kind of thing because they're sort of trapped in these states. They're not free to take any states like a free particle. Anyway, that's these, and the other component of the energy is of course the state in the z direction it's actually in. And as we saw with a 1D quantum infinite square well, we get that the energies are literally given by this. Where now there's this one integer and everything else is fixed. You can of course change this number if you would like these numbers to be, related to these numbers or something, or you want this to be low or high, which is like the reason I'm saying this because it said it in the last slide. I don't know why you'd actually need to change this. I guess that's what this problem is for, so you can learn about this. Anyway, you could change d, of course, the thickness, or you could change what else could you change? You could change the materials you make so that the bands are different, so that these m's are different. You can't really change the momentum levels because they can just be any momentum you want in the x and y direction. They're just free, just like they're free particles in a gas. They can move wherever they want. You can, of course, change the energy levels, but there's only, you can only fit so many in each state. These are all constants. This is m again. I guess this is probably m star. Anyway, whatever. So that's that. So we're literally adding the kinetic energy of 2 dimensions and the potential energy of 1 dimension because those are the only, really it's potential plus kinetic of all dimensions, but they don't have them in the other dimensions, so. Okay. Does that all make sense? Does that all make sort of qualitative sense?
Makes sense.
Because when he, again, like I said this before, but when I first started the class, when I talked to Dr. Z, he said, I want everyone to understand this qualitatively. And I know that especially in the second semester, people will have trouble following all the math and doing all the problems. But I do want them to really make sure they don't give up on understanding it qualitatively. So hopefully, that is what you need to do all the quizzes, which I will get back to you on what is actually on them.
Saving grace.
Okay. Anything else?
I have another question.
Sure.
The acceleration of an electron. I don't
Yeah.
remember learning about that.
Yes, because we did not.
Okay.
Actually, I mentioned it for 1 second yesterday.
Okay.
But that's the point of that is that it just has to do with the what is that? A letter?
Then.
M. Yes, it's a. So M was the effective mass, and we got that by it's h bar squared over d squared k. No, d squared e d k squared maybe. Anyway, whatever. It's just the effective mass. So and going back to if you remember, so obviously we know why we did the effective mass, but if you look at the formula, whatever, you get this. The point of the acceleration part of the point of this question is to get you to realize that this effective mass is literally how it works. So in this system, we already know that we have some effective mass m star, and that means that because of F equals ma, A you can write as F over m star, right? That means it will literally, I'm actually going to turn that light back on because I think on the video it shows up kind of dark. I went to sleep. Hopefully it's still recording. Yes, it is. Okay. So we have some effective. Oh, sorry, I just turned that back on.
Okay,
Yeah.
okay.
Yeah. No, I understand. This seems very creepy. So if F now, what you might think, what forces are we going to apply to these electrons? Like what kind of force? And the answer is the electric force. That's kind of the only thing you can do to an electron, is apply the electric force. The electric force is given by an electric field, and F equals E, which is the charge of the electron, times capital E, which is the electric field.
Okay.
We didn't talk about that, I don't think, at all. But in a physics class, you would learn all about the electric field for 6
So
months. But
the acceleration equation in the book
yeah.
has E negative.
Oh yeah. Sorry, because yes. Thank you. That's a very good point. The electric charge of the electron is minus E, because electrons are negatively charged, of course.
Got it. Okay.
So that's just a convention. The convention is that E is plus a positive number, something 1.7 times 10 to the negative 19 coulombs. I literally just made that up, but I think that's right. Is that right?
Not off the top of my
That sounds right.
It's something like this. Coulombs is, of course, unit of charge, right? But the convention is that E is a positive number, so minus E. And actually, that makes sense because electrons, if you turn on an electric field, electrons go the opposite direction of those. So if you turn an electric field going down, the electrons will go up because they go the opposite direction of positive charges. So anyway, and so that's it. So this is the acceleration of an electron in this material where it has this.
So E
yeah.
is that equation right there, that long equation you
Oh no! Sorry. This is an electric field.
field.
I should write it as these are all vectors, of course.
Okay.
You don't need to use components and stuff, but this E is
So
electric
how-
field.
Okay, so the question says So calculate the acceleration of an electron in silicon.
Uh-huh.
So E, the vector E.
Wait, sorry.
So that's what E.
Oh,
equals.
yes. Okay, so in the book they use curly E.
Yes.
Yes, okay, thank you. That's a good, curly E just means the electric field. So they tell you the electric field is 1 volt per meter, I think, right?
Yep.
That's actually equal to 1 Newton per Coulomb. Fun fact. This is actually probably a better, this is a better one to use.
Okay.
So,
Oh, because the E electron is in Coulomb.
yes, exactly. So
Okay.
then you multiply it by E, which is whatever I don't trust what I wrote, just look it up. But
Okay, yeah.
1 point whatever minus 1 point whatever something coulombs, and you get something in newtons. When you divide newtons by kilograms, you get meters per second squared. So that's exactly what you want to do. So of course you need to find what m star is now for silicon. So
Yeah.
now the problem just becomes m star in silicon.
Yeah.
Now how are we going to do this? I have no idea. I think it might say somewhere.
So,
Oh, there we go.
oh, so we can look all this up, right?
Yes. Oh, thank God.
Online.
Thank God. Yes. We can look all this up. So it's either online or ideally it's in the book.
So well, hold on. It says silicon. Oh yeah, all of them are.
Yes, and I believe.
Yeah, all of the 3 that we have to do are in the book. But I know
Perfect.
there was a previous example where it asked for multiple. It was these 3, but a whole bunch of other ones.
Yes,
And we had to
you had to look
up,
them
yeah.
up. Yeah. Let me just make sure the directions are right because. Okay, so they don't say directions, but they. How much energy would it?
So we calculate the acceleration and then the energy have.
Oh, I see. Okay, so yeah, okay. So they give this to you in the book. I think
Yeah.
they divide it by like m perpendicular and stuff like that.
Yeah.
I think they just mean whether you apply.
There's multiple.
Yeah, I think what they mean is because if you apply the electric field, so imagine this is your sandwich electron gas.
Yeah.
If you apply an electric field this way or this way, it has a different effective mass than if you apply it this way or this way.
Yeah.
Because if you apply it down, it's like shoving it against this insulator. It's going to have a lot more mass, it seems like, right? But if you do it horizontally, it's going to be sort of relatively free. So it depends on the direction. So I don't, that's what I was just reading the question. They don't actually say, but I assume they mean in the XY direction. So it would be the,
Well, the
parallel.
equation, it says bottom of the conduction band, and there's a m star COND.
oh, okay.
And then the equation for acceleration has that.
Oh,
So
okay.
I assume we would use that
Yes,
one.
then use that one. Yes, good, excellent. So yes, and then so then it, of course there's different. Yeah, as you said, this is a little more detailed than just m star, but use the one that's
That's,
on the next
yeah.
page of the book or whatever. And
So how much,
sorry, what was the other thing? Oh, the energy.
how much energy would it have so many seconds later?
Right. So the key thing there is that because they said it starts at the bottom of the conduction band, that just means it was at rest.
Yes.
And then it was exposed to an acceleration for however many seconds it says, 10 to the minus 4 seconds. Then it's literally just a kinematics problem. Then you could just say, I had an electron, it was at rest, and now it had, after time t, what is its new, it's just v final equals v initial, which is 0 times a t, right? And then I have v final, my final velocity, but then I can just find the energy final is just equal to 1/2 m star, again, vf squared, right? Because the initial energy was 0.
Got it. So we have to. How much energy? So where does the time? Oh, so to find the final velocity, we use the time times the acceleration.
Yes. So this is
Got
just
it.
kinematics now.
Yep. Okay.
That's what the rest of
And
the
then how
problem is.
fast? Wait. So it says how fast would the electron be going at this time? That's the velocity.
That's v. Yeah.
So it asks that question after the fact.
But
But you would need to do it in
You're right.
reverse.
That's confusing.
That seems right up his alley.
I'm just now I'm suspicious that maybe there's another way to find the energy. Let me look. I don't think there would be anything wrong with doing it that way. You bring up a very good point, which is that
Yeah. So here is
they say for silicon, so
Well, so here's kind of where they talk about the acceleration.
okay, yes. So for silicon electrons,
So it would be this one, right? Because that's
Yes.
the-
yeah.
How will we know?
I would just say just use this,
Okay.
even though it's backwards. So, I should also mention
What's
the fact
Is
that in the table it gives you M star conduction over M naught.
Yeah,
This is the
0.
no, this is the mass of the electron, just the mass of the electron.
Okay.
So this is like 0.6 or whatever.
Mm-hmm.
That doesn't mean it's 0.6. It means that if you divide it by the mass of the electron, you get 0.6. So you make sure you have to fill this in too.
So we need to.
So in other words, to find M star cond.
They don't give you MO though. But this doesn't have.
Oh wait, sorry. This is the conductivity mass.
But in the question it asks.
Oh, it says conductivity mass.
Oh, conduction.
conduction band.
Oh. So
No, that's
different.
probably the same thing. I think that's the same thing. Yeah.
So we would use that one then, or do we have to find it with the? Because I don't. Doesn't tell you kind of how.
Yeah. Let me just make sure it says M naught is. Make sure it says M naught is the rest mass of the electron. I'm not going to be able to find. Anyway, I'm sure that's true because of course that's true. Yeah. So just make sure. Sorry.
But it's
Oh yeah.
this one.
So. Okay, because they say conduction band, I assume this is what they mean, this M con. They do, so let me just overview these real quick, even though these aren't specifically in the question. Oh, I didn't mean to erase that. Well, anyway, they give you, if you look up, they give you M star parallel over M naught, and they give you M star perpendicular over M naught, and they give you M star con. I'm putting the stars in a weird place, but whatever. M naught is like 1 point, what's the rest mass of the electron? I forgot. Anyway, it doesn't matter. It's the mass of electron. If you Google mass of electron in kilograms, it's that.
9.11 times.
That sounds right.
10 to the negative.
Something in kilograms or whatever. Yeah.
Yeah.
So that's M naught. So if you want, and then A is just going to be F, which is, in this case, F, I already know what F is, it's minus E over M star.
So you just.
Then you have to actually solve for, so if you want the,
So we do have to divide it by them.
yes, in other words, if M star con over M naught is 0.27 or whatever it is, you have to multiply 0.27 by M naught. And
Okay.
then you'll get this to plug in there, yeah.
So it's the M naught or the M cond that we need for this.
Yeah, yes, I think. So first of all,
Okay.
that's fine. But the reason that it's a little confusing is because in the question they specifically say in the conduction band,
Oh,
and I'm
okay.
assuming they mean that's what this cond means.
That makes sense.
The other things are M parallel and M perpendicular, and I assume this just means. Well, I don't have to assume. I know this means that perpendicular would mean into the sort of the walls of this, which would be kind of a silly thing to do, and parallel would be in this way, but cond would be specifically in the conduction layer. These aren't regular. These would be sort of non-conduction electrons, right? The masses of
Yeah.
non-conduction. This would be the other bands. The conduction band is as we know just defined to be the highest band that's not fully occupied. So it's the one where the conduction will happen in. So I think that this is like the one you basically always use. Because you kind of always, with silicon and all this stuff, you're always considering conduction of electricity. So you'd pretty much just always use this one. So I would say because they say conduction band, you can use this.
Okay.
You'll notice that in that table, they talk about holes. Remember I talked about that before?
Yeah.
How there's electrons, electron holes. That's just whether it's a p-type or n-type
Yeah.
semiconductor. That will not, I don't believe that will come up, except, I don't think that will come up because he hasn't said anything about it. And it's just that you just know that when they say holes and you're like, what is that? Like a particle called a hole? And yes, it kind of is a particle called a hole. It's just a positive. It just means that the conduction bands are sort of conducting holes where electrons used to be, or something. Anyway, there's a whole field you could look up about this subject that I don't participate in. So anyway, yeah. So also just the one of the reasons I noticed this was that this has no units. So if you want A to be in meters per second
Got
squared,
it. Okay.
you need
Need
this
the-
to be in kilograms so that you can have this in kilograms.
Got it.
Or you could put it in electron volts, but then it'd be kind of then you'd have to, anyway, just do everything in newtons. It's better to do it that way. Because I don't know how you divide volts by electron volts. I don't know how that, they're not the same measurement, of course, but I don't know what it comes out to be, so.
One last question.
Sure.
It says how many conducting electrons are in 1 centimeter cubed of copper, or just
Yeah.
any element. How would we? 1 centimeter cubed.
I think what you can just do is you don't have to do any of this. You can just say
So I'm overcomplicating.
1 cent, I think.
Okay.
Actually, let me look at it.
It just says how many.
Oh, this one.
Yeah.
Oh, yeah. So what you can do here is just say 1 centimeter cubed of copper has how, I don't know why I'm writing this down. It's just a sentence. How many protons? Do you think you could do this problem? This would just be a,
You guys are in charge. We're heading out.
oh, okay.
See you
All
tomorrow. Bye.
1 centimeter cubed of copper, how would you find that out? You'd have to know the
Yeah.
density of copper. Then you'd have to know how many moles per, this is where I
So,
stop. I can't even.
Grams per mole, right?
Grams per mole, all that stuff. And then once you have the moles, you know that a mole is this many atoms. And an atom of copper has how many protons. Once you know that, it will be exactly the same number of neutrons. As
Electrons.
electrons. So
So atom, no, because 1 atom equals 1 electron.
no, one
No.
atom is,
Proton equals 1 electron. Not 1 atom equals 1 electron.
So 1 proton.
1 proton.
one proton is 1 electron. So
So
copper has, 40 or whatever.
So wait, you go from
I don't think
density
that's right, but
to grams. Okay.
Sounds like
So once you get to atoms to mole, atoms.
yeah. So go from centimeters to grams,
Yeah.
from grams to moles,
Uh-huh.
from moles to atoms,
Okay.
and from atoms to protons.
So
Okay.
you have that many atoms, you multiply that by the amount of protons in copper, and then that's how many electrons
Yes.
you have.
Which is not 40.
I don't think
33? Does that sound right?
It sounds like I don't know.
Or no, maybe it's higher. Maybe it's like 50. Anyway, I don't remember. The other one, and they ask for another element, of course. The only difference there is going to be, oh no, not the only difference. The only difference is going to be the number of protons per atom, but also the density is going to be different. So you have to look up density of copper, because that's not, you can't figure that out from anything like known. You'd have to like literally look it up.
29 protons in copper.
Oh, 29. All right.
Magnesium is 12.
There's 27 electrons.
27
I was gonna say,
electrons?
they're not generally even.
It's
Wait.
because of the charge. Copper has a
Copper is
plus 2.
3.
Copper ion with a charge of plus 2 has 29 protons.
Yeah, but they're asking about just regular copper, right?
Yeah, but that's regular copper. This is getting into
Like
chemistry.
calcium has like a plus
Plus
2
2.
always. That's like its normal state.
Mhm.
Yeah, but if they just said a block of calcium, I
It
would
would
not
still
assume
have a
it's-
plus 2.
so it has an electric charge,
Yes.
like a block of calcium has an electric charge? Block of copper has an electric charge?
I believe so.
According to the chemistry
Yes.
behind it, based on the number of electrons and protons. Copper
Huh.
I
always
assume
has.
for this,
I'm-
we
I am
can
making my
assume it's
suspicious
even,
face.
But
I assume they, first of all, for the problem, I
Chemistry
think they
is
want you to
different,
assume
though.
it's
but
even.
chemistry, yeah, I'm pretty sure copper.
So really, when you have just a metal sitting out,
Copper's atomic number is 29.
But doesn't always mean that's the same metal.
I know that in
I think
ions,
it
of
means when it's
course.
bonded, it has a +2 charge, but separately, like just an atom of wow, that was weird. An
It's-
atom of copper has 29, but when it's bonded with something, it'll have a +2 charge.
Sure, but
Because of how
metallic
many
bonds I
electrons
don't
it
think
shares.
are ionized, right?
Because of how many electrons it shares with the atom it's bonded with. It's like those electrons share like on that atom more often than they share on copper, so it's +2 charge because it's lacking.
Sure, but in a metal, they just have metallic bonds which are not ionized, right? They're not like ions. Anyway, I don't know. It doesn't
That would
matter.
make
The
way
point is,
back in
for this,
chemistry.
they probably just want you to use this atomic number.
Yeah.
If you use a different one, I will mark it right. It'll be totally fine.
Well, the atomic number is 29.
Yeah.
Which is with the +2 charge because that's only 27 electrons.
Right, but he's saying just use the 29 electrons because
I assumed
he's
you could just-
assuming that copper is.
Oh, got it.
I'm assuming that that in a block of copper, the net charge, if you just made it 0, which we can have a
When you
debate.
make the net charge 0, I'll give you that.
Yes. Then it will have the same, of course, by definition of net charge means all the electrons in it have a corresponding proton.
Yes. But not all.
However unrealistic, you could.
You and I will not let this go.
All right. You're free to do it as
Lie on
realistic as you
people.
like.
Yep.
But yeah, that's what. The reason I'm just saying that, like, that I'm pointing out that this is like completely not the same as like this is nothing to do with bands.
Okay.
Yeah,
Of
where
course-
did this come from?
Because
I have
like,
it's
I don't-
question 1. That's why I know it's simple. So I think they want you to realize that, like, yes, we're doing all this stuff with bands and stuff, but I can still just count the electrons if I want. Like, if I don't care about which band they're in or what is the structure or whatever, I can actually just count the total electrons. I don't know why anyone in the world would ever want to do that, but you could.
Got it.
Well, you could, and then you perhaps would be wrong because you use the atomic number instead of the actual number of electrons. But anyway,
Cool.
all right.
729.
Look at that. Wow, exactly 7:30.